Problem 9 is about counter currents, and essentially at the end of the day it involves doing a bunch of algebra. So this is a simple model for the counter current in an artery and vein. So you got your artery going out. Um, your this is your capillary, if you will. So your arterial blood flows in, venous blood flows out. And as you move out through this capillary, we've got TA of X. So we're going along the capillary, and it comes back along itself to create, to give you the counter current balance that you want um, in terms of what's going on with the temperature, right? Um, and so here's a model for that, right? TA as a function of X is some constant that you come in at plus the difference across here times AX. And it's just a linear fall. The presumption here is this falls linearly and rises linearly as you come back. And so first part is to determine C1 and C2 in this model, right? In terms of TW, which is the temperature of the, what's TW? Right. Whale's body, TW. TC is the temperature of the ocean, and A is the length. No, A is the, what is A? Where is A? Okay, we'll get there. Um, and then L, the length, right? Okay. And so we've got to just basically find our boundary conditions, if you will. So what are they? TA at 0 is going to be the temperature of the whale. So when you start off here, the blood's at the temperature of the whale. Well, you put in 0 for X, and the second term wipes out. And so C1 is clearly just the temperature of the whale. When you get out here at the end of the capillary, or at the bend in the capillary, right, you've reached ocean water temperature. Right, so TV of L is TC. Well, that's C2 plus C2 minus C1 onto AL. And you can solve all this and do some algebra, and you can get an expression for CT, C2. C1 simple, that's TW. C2 is TC plus TWAL over 1 plus AL. All right. And so C1 and C2, we have expressions for those. So we've done part A. Plot these. Right, so I may have done this, but plot these. They're linear functions as you go out. The heat loss from the body and the surrounding area is proportional to delta T, TA of L minus TC. All right, so you're going out, you're out here where things happen. All right, TA minus TC, TA of L minus TC. So find an expression for delta T. So TA with C1 and C2 stuck in is this. TV of X with C1 and C2 stuck in looks like this. Delta T is just TA at L, right? So I stick in L for X, and you get, this is delta T minus TC, right? And they want AL large, you can work through that, but what was the question? I've lost myself in kind of playing around with this. What does temperature drop across the capillaries due to the heat being lost to the water? All right, so we've got all of our values, TW, TC, A, and L, and we're asked for this temperature drop due to heat loss to the water, and that is this delta T. All right, so we're looking at plugging in all of our values into delta T, which is going to be proportional to the heat loss, right? And so this then, what's happening again, arterial blood's coming out. As it goes out, it's heating up the venous blood coming back. All right, so it hits here, and you've already lost heat from the arterial blood to the venous blood. And so it's going back into the body rather than all being lost out here at the end where you're doing the heat exchange with the water surrounding you. All right. So good bit of algebra. Get to your expressions for C1 and C2. Get to your expression for delta T. And once you're here, it's a matter of putting in the values and just doing the calculation. And I believe that is it and gets us to the end of problem 9.